Hello everyone, I will now present our E575 project, which is about accelerated MRI via optimized nonlinear ultrasonic gradient encoding. As an introduction, we need to talk about what's a nonlinear gradient. It's an extramagnetic field whose strength varies with position in a nonlinear way. So why might a nonlinear gradient help? It gives us the scanner an extra and an independent way to label points in space. For example, there have been papers about these nonlinear gradients, for example, Patlock and O-space papers, but they use nonlinear coils as a slow source of encoding. In our case, we will do a similar thing to an ultrasonic gradient paper, which they use the ultrasonic gradient in the readout duration. In our setup, we are also using a ultrasonic gradient such that its gradient bandwidth will be between 20 kHz to 75 kHz. But it will also be in the readout during the readout, but it will be in the nonlinear gradients and it will be multiple channels. So our assumptions about this project is, first, the nonlinear gradient field maps are known exactly. That is the most restrictive assumption because that assumes that there is no motion, so that the gradient maps are not changing with motion. Second is the coil sensitivities are known exactly because we are using sense reconstruction. The driving currents are known exactly. The gradient amplifiers, of course, needs to be have a 75 kHz bandwidth. We are not looking at any B0 inhomogeneity, off resonance, or chemical shifts or susceptibility effects. We are not looking at any eddy currents or any concomitant field effects. And in our study, each loop's axis is fixed parallel to the z-axis to have zero torque. So the theory about this is about the measurement we have while the MRI runs. So, for example, with C receive coils, each of them has some coil sensitivity. We have some complex spins in this row here. And each voxel has its own phase. And if we sum over each voxel given their area, we will have the received measurement. So that phase becomes our only source that we can encode our nonlinear gradients in here. It has two parts. First part is the conventional gradient part. It has the conventional Fourier transform encoding gradients, Kx and Kz. Kx here is the readout gradient, and Kz here is the phase encoding gradient. And the nonlinear phase part, which is due to the nonlinear coils. Each coil has some B fields of the end coil at position R for 1 amperes of current. This is the Bn of R. And each coil has some current waveform with respect to time. And its integral from 0 to t gives us the moment of that coil. And when we multiply it with the B field and sum it up for all of the coils, we get the nonlinear phase. So first question about this project is, how do we optimize the coils? Given that we have C amount of coils, where should we put them and how big should they be so that resulting fields encode the imaging slice as informatively as possible? So what we do is we first compute each loop's fields and their gradients. Then we write them in this matrix form. What we are trying to do is make sure that the column vectors here are as different from each other as possible. So we multiply it with its transpose, and we are looking at its log determinant. And of course, this is a per voxel measurement. Throughout the whole image space, we need to find an aggregate score, for example, 25 to 25th percentile. And well, for that score, we are optimizing with respect to the coil radius and position for each coil. Okay, so here the code is running a genetic algorithm to optimize the two coil positions and their sizes. And it is logging the information score we derived with respect to iterations, and it's trying to maximize the information we gain from different coils. Next target is the current optimization. So now that we have optimized coil positions, how should the currents be? That's the question. So what we do is we simply set the current waveform as a linear combination of sines and cosines, and we are trying to find the weights of these sines and cosines. We limit the maximum current by limiting the maximum 90th percentile phase these coils will generate. And we will optimize the rank of the forward matrix with respect to these the sine weights, sine and cosine weights. It's subject to the 90th percentile phase, nonlinear phase limit to be the some limit we have chosen. Let me continue with the demo of that. So the coil optimization has found this converge on this two coil setup at each end of the phantom. Okay, so it will again run iteration of some optimizer, Aydın optimizer in this case, and it will look at the rank with some cutoff chosen to be at R equals 8 only linear gradients. So we can compare it with that case. So if the rank reaches 496 for a 64 by 64 image, then it will be certain that we can reconstruct the image for R equals 14 case with these nonlinear gradients. So this whole iteration is doing this, all optimization is doing this for R equals 14 case with the given iterations current waveforms here. Actually, let me move this so it is seen better. Yeah. So it will run this iteration until it converges once more. So let me go to the next stage, which this animation shows each coil's phase in the phantom space. So in a 50 by 50 centimeter space, it's showing the phase, accumulated nonlinear phase of each voxel with respect to time. So you can see that it is using the nonlinearity of each coil to its maximum potential because it's running, for example, this to forward, this to back, and it changes them and it runs them both at the same sign, for example. Yeah, that's in reconstruction. We are using something called conjugate gradients. It's an iterative method for solving Tx equal B matrix equation when T is symmetric or Hermitian and positive semi-definite. At each step, it picks a new search direction, so it's conjugate to all previous directions, and it computes the exact step length along that direction. It updates the estimate, and it is guaranteed to converge in at most n iterations. So for our case, 4096, I think. And the conversion rate depends on the spread of the eigenvalues, so that's the condition. Okay, so all of these are running in the GPU because the iterations takes a lot of parallel compute, and it takes a lot of time in CPU, and it needs a lot of iterations. Like I said, it needs like 4,000 iterations to optimally converge, but you will see that it converges approximately.
So, the optimized conditions as coils. We make this optimization for a different number of coils and find that 5 coils gives us the highest rank for the forward matrix in our optimization problem. So here are the magnitudes for our 5 coils, the gradients fields generated by each coil in the x and z directions, and the total gradients fields. And here are the currents generated by each coil for one voxel. The frequencies change from voxel to voxel, and the current at the median voxel is shown on the right, which is the line we will trace through case space. Dashed lines show the conventional linear phase encoding lines, and you can compare it with that. Here are the results for different acceleration values. The left column shows the conjugate gradient sense reconstruction for a linear phase. The middle column shows the nonlinear layer conjugate gradient reconstruction, which includes the nonlinear phase for a single coil, and the rightmost column shows the nonlinear version for 5 coils. With 14 times acceleration, when we add a small amount of noise to the bottom row, we can see that the distortions in the nonlinear reconstruction are more apparent. The linear construction gradient seems to be more robust to noise addition. So this is better seen with error maps. The nonlinear gradient has higher SSIM for larger acceleration factors. However, the linear conjugate gradient reconstruction performs better with noise. The linear ultrasonic conjugate gradient is good for acceleration and noise. The nonlinear ultrasonic, however, has advantages of focusing the gradient field at certain regions of interest. The performance of nonlinear gradients would increase for higher oversampling rates. Right now, we're oversampling by 4. And a limitation for nonlinear ultrasonic gradients, however, is that we need to know the exact field map for reconstruction. When a small noise is introduced to the system, perhaps with patient motion, the method will not perform as well. And for that, we can recompensate this motion with a neural network that infers the per voxel field phase pattern to track the gradient field and therefore the motion of the patient. In conclusion, nonlinear gradient encoding allows acceleration factors up to 14 without visible distortion, and comparing ultrasonic gradients of nonlinear with linear encoding, we can see that local gradient strength determines the reconstruction accuracy of the method. So by increasing the local gradient strength with coils and amplifiers, we can reach higher acceleration rates.
Result that's mostly converged, so you can see that with the no extra gradient, it was not that greatly reconstructed. It had a lot of artifacts, but with our ultrasonic nonlinear gradient addition at R equals 14, we were able to converge reasonably at around 2000 iteration to this figure here. Thank you for listening.